This is regarding the module gas liquid chromatography. So dear students, let me introduce myself. I am Vivek Sharma, Principal Scientist working in the Dairy Chemistry Division of National Dairy Research Institute. So today I will be discussing with you one of the very important, familiar and versatile techniques in the field of chemistry, that is gas liquid chromatography, which is in short, or its a popular name is GLC. So this technique is based on a principle of partition chromatography. So during my lecture, I will be telling you about the basic principle of gas liquid chromatography, then the components involved in the gas liquid chromatography, little bit about its application, and then its working. Thank you. So let us have the introduction, or we can see what the gas liquid chromatography is. Now, this gas liquid chromatography, the first account of it was published by the author Clayson in 1946. It is very powerful technique which is commonly used to separate different components of foods as well as compound of organic nature. It is used for both quantitative as well as qualitative analysis of food components. And this technique is based on the principle of partition chromatography, wherein the components are partitioned between the liquid stationary phase and a carrier gas mobile phase. So as I said that it is based on the principle of partition chromatography. So it involves two active parts. One is mobile phase, which is an inert gas, and another one is a stationary phase, which is a liquid coated on a solid support like silica. The basic requirement of GLC analysis is that the sample should be in vaporized state at a temperature below 350 degree Celsius. So that means we need a vapor, plug of vapor. The components of vaporized sample are fractionated and separated according to partition coefficient between the gas and liquid stationary phase. So that is the basic principle of your gas liquid chromatography. Now as I said that there is one mobile phase and another one is stationary phase. So the stationary phase, as I said in my earlier slide, that it is a liquid state. So it is a liquid material which is coated on finely divided inert solid support, which can be porous polymers, which can be diatomaceous earth, it can be silica. So this is basic or very important component of gas liquid chromatography. And these stationary phases are packed inside the columns, which can be capillary, which can be your packed columns. And these stationary phases are of basically two types. One is the polar and another one is the non-polar phase. So from practical point of view, we can see in this table where the stationary phase has different polarities. It can be completely non-polar, it can be slightly polar, it can be medium polar, it can be your polar or highly polar. For example, 100% dimethyl polysiloxane. So it is a non-polar kind of stationary phase and it is preferred for petroleum products and saturated hydrocarbons. Now similarly, for example, polyethylene glycol. So this is a polar phase which is preferred for fatty acids, flavor and alcohols. You can say these stationary phases, they have different temperature maxima. That means they can remain stable up to certain temperature and afterwards they start degrading. Now the basic principle of selection of these phases or stationary phases is depending upon the type of material we want to separate or we want to analyze. For example, if we have a polar material, now that will more stick to the polar stationary phase and will be eluted at a later state. Now for example, we have the material or compound which have different functional groups, what are of similar boiling points. then polar phase is generally more suitable. Now, we have seen the stationary phase, which is very important for separating any compound or analysis of the any compound. The another thing I want to introduce to you is the commonly used terminology in gas liquid chromatography. As in case of any other technique, here also we have some very common terminology which is used during the study of this technique, and very important one is the retention time. Now, this retention time is denoted by letters small t and capital R. So, as the name indicates, that means something is retained and eluted after some time. So, that is basically the time required for the maximum for a solute peak to reach the detector in a gas chromatographic column. So, that means this is the maximum part of the solute will be eluted, or it is the time taken for a solute to elute to the maximum concentration, that is known as retention time, and this is very important parameter in gas liquid chromatography. Most of the time we identify various compounds on the basis of this retention time, and it is generally seen that every compound or every component has usually different retention time. So, another thing is the retention volume. Now, this is basically, as the name indicates itself, it is denoted by VR, and it is the volume of the gas required to carry a component maximum through the column. Another very important terminology which is used in the study of the columns, that is the column efficiency. Now, this column efficiency, it is basically an indirect measure of peak width at a specific retention time, and this that is the column efficiency. Now, this column efficiency is basically you can say find this by way of theoretical plates, and these theoretical plates, as the name indicates, these are the theoretical kind of thing. That means, when this number of theoretical plates of any column is very high, then the efficiency of that column is also considered as very high. This is basically a concept, as I said in my previous slides, that in GLC, when vapor is injected, then this gaseous state is passed through the column, then the components, when they pass through the column, they form very small plates, and these are called as the theoretical plates. That means, more is the number of plates, more efficient will be the partitioning and more efficient will be the separation of the compounds. Another terminology which is very common in case of gas liquid chromatography, that is the capacity or retention factor. Now, this capacity or retention factor is the velocity of analyte relative to velocity of mobile phase. In my previous slide, I have told you that these were the important terminologies which are used for identifying the compounds, which are used to find out the efficiency of the columns. So, next is a little bit about the application of GLC. So, my dear students, the GLC is one of the techniques which is applied in almost every field of science, whether it is agriculture science, it is agriculture industry, it is food industry, it is environmental field, forensic field, it can be biotechnological field, it is perfume and fragrance industry to assess the quality of the butter, and the ban and controlled drugs analysis in urine, blood, tablets and energy drinks, etc. And the very common example is in case of agriculture field and in food products, the analysis of pesticide residues. In case of analysis of pesticide residues, GLC is the technique which is very commonly used to find out the amount of pesticide residue in any food products. Similarly, in case of agriculture industry, if someone is extracting some oil to find out fatty acid composition, to find out its flavor profile, the GLC is very commonly used. So, that means GLC is used in almost every sphere of chemistry and every sphere of science, and it is very much related to our life. That means, whatever the food products we are eating, whatever the fragrance or the perfume we are getting, in our day to day use, those all are tested by this very important and versatile technique, wherein we will discuss the instrumentation in the GLC. Now, so far we have seen the basic principle, we have also seen the different terminology used in the GLC. So, next is the important component is the instrument of GLC as such. So, as the name indicates, gas liquid chromatography, that means it is a kind of chromatography where we need gas, we must have something liquid, and then by making use of this gas and liquid, we are separating the components of food or any other chemical compound. So, that means in GLC we have a mobile phase, that is a gas which is also called as carrier gas. So, the carrier gas that is generally should be inert, and then we have a gaseous mobile phase, must be inert, as I said. It can be helium, it can be nitrogen, it can be argon, it can be hydrogen. And then another thing which is there in the GLC are the different type of the filters, oven, injectors and detectors. So, all these we will discuss one by one in the subsequent slides. So, let us move to the next slide. As I said that in case of GLC, the gases are very important, that is the carrier gas is very important, and use of carrier gas also depends upon the type of detector we are using. For example, in case of thermal conductivity detector, which we will be discussing in the subsequent slides, the preferred gas is helium. For flame ionization detector, the preferred gases may be helium or nitrogen, and in case of electron capture detector, the gas preferred one is the very dry nitrogen. Now, we are moving to the next slide, that what is another very important component in the GLC. That means, now we are using gases. So, the flow of the carrier gas very important for the efficient separation of the different components in a mixture, and this flow of carrier gases is generally measured by a flow meter, or nowadays the machines are coming up with automatic flow control valves. So, one can control the flow of the gas, and this flow of the gas is again dependent upon the type of columns we are using. For example, if the columns are wider in nature, that means they have the more OD and ID, then the higher amount of gas is required. For example, if 1 by 4 inch is the outside diameter of a packed column, then the requirement of the gas is 75 to 90 ml per minute, that is of carrier gas. And in contrary, if the size, that is the internal diameter of the column is 0.25 micron, that is very small column, which is also called as a capillary column, then the requirement of the gas is reduced considerably, that means only 0.75 ml per minute. So, that means depending upon the flow of the gases and depending upon the type of the columns, we can get the very good results what we want to achieve. Now, we are using the traps. Here I am discussing about various traps which are used in the gas liquid chromatography. Now, since we are using gases in gas liquid chromatography, so general requirement or principle is that these gases should be very pure or highly pure in nature. Though the companies from where we procure these gases, they take care of these things, but now the facilities are available, instrumentation is available, where we can be doubly assured. So, that means different kind of traps are being provided by the gas liquid chromatography manufacturers companies, which are known as traps or the trap devices, which can trap the moisture or which can trap the impurities present in the gases. For example, for nitrogen, there is a nitrogen trap where the moisture trap, that means that traps the moisture, and oxy trap, which can be the regenerable silica gel. For hydrogen, we can have a moisture trap which can be activated charcoal. For zero air, there is also a moisture trap which can again be a regenerable silica gel, and for helium we can have a moisture trap and hydrocarbon trap which can be activated charcoal. So, once we make use of these traps, then we are doubly assured that the gas which is passing through the machine, that is the gas liquid chromatograph machine, so that is very pure and that will improve the efficiency of our analysis. Now, in gas liquid chromatography machine, there is another important component, that is the injection system. As I said that in gas liquid chromatography, one has to use the sample which is readily converted into the gases. So, there can be liquid sample or there can be solid sample. So, depending upon the type of the sample, we can have different type of the injectors. So, the requirement of GLC that sample should be injected immediately, should be converted into gaseous state before entering the column, or in other words I can say that the suitable amount of sample should be injected as a plug of vapors. So, therefore, for liquid and solid samples, differently designed injection systems are used. So, for liquid samples, the injection system is the micro syringe. Simply by making use of micro syringe, which are specifically designed for the GLC applications. So, sample is injected in the injector and which is easily or quickly converted into the vapors, and those vapors then pass through the columns. In case of solid samples, we are using generally the thin glass ampoules which are placed in the gaseous stream and then crushed. So, that means heated material is then converted into the vapors and then it is passing through the columns. Now, as I said that for gas liquid chromatography, the sample should be in a vapor state. So, some of the material they are highly volatile, so they do not need any treatment, but some of the materials they are not that much volatile, one has to make them more volatile. So, the derivatization is generally preferred. For example, in case of fatty acids, methyl esters are made to make them more volatile, so that easily they are converted into the vapor, because the requirement in the GLC is that they should be quickly converted into the vapors, then only the resolution or the resolving of the components will be very efficient. So, there are two type of the injection system that we will be discussing in the next slide. So, these injectors, as I said, there are two types of the injectors. One can be the split type of the injectors, another one is the splitless injectors. Now, split type of injectors, as name indicates, that means they will be doing the splitting of something. So, that means these injectors are required where a portion of sample is introduced in the injector and majority of it is vented to waste. So, that means this is required in the applications where we need very small amount of sample should pass through the column. For example, if we have the very high concentrated samples or the samples which are to be fed to the capillary columns, because the ID or internal diameter of the capillary columns is very small. So, very small quantity of sample needs to be injected. To have the accuracy, it is difficult to measure or it is difficult to syringe out very small amount of sample. So, for that purpose split type of injectors are used, where we can inject slightly higher quantity of sample which is automatically split into two portions. The major is removed as a waste and only part is passed through the column. So, there you can fix the ratio of the split. It can be 1/10 of the material which should go inside, it can be 1/50th of the material which will go inside, it can be the 1/100th part of the material which will go inside. Another type of the injector is the splitless injector. So, that means there is no split. So, that means the requirement is that the majority of the sample should pass through the column, and it is required for the material when the concentration of active components is low, typically for trace component analysis, and generally this splitless detectors are used in the packed column. So, that means when we are using packed column or wider columns, then we make use of these splitless injectors. So, these injectors are also very important because they affect the efficiency of our gas liquid chromatography analysis. we will discuss about the columns. So, the another very important component in GLC is the column, because whatever separation has to be done, that is performed inside the columns. And these columns, as in one of my previous slides, as I said, that the stationary phase is filled in these columns. So, these columns can be of two types. One is the packed columns, another one is the capillary column. So, in this slide we can see the packed columns, they can be made up of glass or they can be made up of metal, as it is evident from the photograph that they are smaller in size, but they are wider in diameter. So, these are the packed columns, and another one is the capillary column. These columns are very thin columns, as the name indicates, capillary, and they have the very large dimension. Some of the columns are even 100 meters long columns, which are coiled together and they are placed inside a cage, so that they can be fitted in the column. They can be made of the fused silica material also, and these columns are used for the analysis of isomers or the separation of very you can say that's components which are very having the retention time very close to each other. So, these columns use depends upon the type of analysis we want to perform. So, these columns are very important in the gas liquid chromatography analysis, and these columns previously or initially people were filling themselves, but now these are readily available in the various catalogs by the various manufacturers, where we will just discuss that what is the dimension of these columns. So, from this table we can very well see that in case of packed column, the maximum length range varies from 2 to 6 meter, whereas in capillary column the length can go even up to 100 meters. But the packed columns, they have low resolving power in comparison to capillary column, and the velocity of mobile phase is also varying. In case of the packed column, the velocity of mobile phase is generally 25 to 150 milliliter per minute, whereas in case of capillary columns, the velocity of mobile phase is 1 to 25 ml per minute. If we use more gas in the capillary columns, then sometimes there is a problem of back pressure. So, therefore, one has to be very cautious while using the columns. If it is a capillary column, it is generally preferred that inject small amount of the material and keep the volume of the gas low. So, this was about the packed and capillary column differences, where we will see the another very important component of gas liquid chromatography, that is also sometimes called as the heart of the gas liquid chromatography, and that is known as column oven. And as I said, it is heart of the GLC because the efficiency of resolving the components in a GLC analysis is temperature dependent also. So, the high precision thermostatically controlled oven is a very much requirement of any gas liquid chromatography, and to have a reproducible retention time and have reproducible result, the control of temperature should be very precise, and this is the heart of the GLC, and the temperature ranges from 0 to 400 degree Celsius. So, that means this column can maintain a temperature of plus 10 ambient to 400 degree Celsius, and it is one of the very important component, where we will discuss the detectors. So, now in GLC detectors, because everything is to be detected by these detectors. So, these detectors are very sensitive and they respond very quickly to even minute concentration of solute exiting from the columns, because the retention time, when we said in our previous slides, so that is the maximum amount of solute which is eluted from the column and reaching the detector. So, that means detectors should be very sensitive, and they should have a linear behavior, they should be stable, and they should have uniform response for a wide variety of chemical species. For any good detector, some are the characteristics. For example, the sensitivity should be high, they should be universal, or they should have a selective response ability to distinguish between species of different components, their response should be rapid, their response should be linear, and they should have stability with respect to noise. That means, they should not disturb the baseline very much and the baseline should not be drifted much. So, that means the detector should be very stable. So, as I said, the detectors, they are detecting the materials which are coming out of the GLC. So, that is another very important component of the gas liquid chromatography, and the cost of the machine of gas liquid chromatography also depends upon the sensitivity and ruggedness of the detectors. So, here we will discuss the types of the detectors. So, there are some common types of detectors like thermal conductivity detector, we have flame ionization detector, we have electron capture detector, we have nitrogen phosphorus detector. So, as their name indicates, they have different principles of their working. So, these principles and individual detectors, some of the individual detectors we will be discussing in the next slide. So, here we will discuss little bit about the flame ionization detector. So, as its name indicates, flame ionization, that means here the material is to be ionized by a flame. So, that means here what we are doing, we are just ionizing the material which is eluting out from the column, and it is a very popular detector because of its very high sensitivity. It is generally said that its sensitivity goes even up to 10 raised to power minus 13 grams per ml of the material, and it has a wide range and greater reliability, and it responds only to organic compounds, and it works on the principle that most of the organic compounds eluting from column, when burnt, they undergo oxidation. So, that means as a result of oxidation, they produce some ionizing particles and electrons as intermediate products of oxidation, and these ionizing particles are quantitatively proportional to the amount of carbon in original compounds. That means, the amount of carbon what is there in the material which is eluted from the column. So, these ionizing particles are collected and neutralized by the polarizing electrodes inside the collector which are there inside the detector and collector, and they generate an electric current which is picked by the electrometer and forms a peak on the recording chart, and as a result of that there is a peak which represent the amount of the material present in the particular compound. The advantage of this detector is that it is a very linear detector, its response is also very good, it has very low noise and it is rugged and easy to use, but everything has advantage as well as disadvantage. So, this detector is also having some disadvantage, that it is a kind of destructive detector. That means, whatever the sample is eluting out and passing through the detector, that is ionized and destroyed. So, that means, we cannot make use of that eluted component any more, and its detection limit is also very good. So, that is the advantage, but disadvantage only is they are the destructive type of the detector. So, this was about the flame ionization detector, which is a very versatile and very universal detector, and many analysis it is being used, whether it is fatty acid analysis, other compounds analysis, it is very commonly used detector and very easy detector to handle. Next one is the thermal conductivity detector. So, as its name indicates, that means it depends or it works on the principle of thermal conductivity. So, this detector is made up of 4 elements, as we can see in this slide. We have shown the diagram of this detector. So, here we have the 4 filaments which are arranged in an electrical bridge network, and the carrier gas which flows around these filaments through cavities. So, that means the temperature of filament is determined by the rate of heat loss by conduction through the carrier gas. So, that means these filaments are heated one. So, when the carrier gas consisting of these elements, it passes through this detector, then it absorbs some of the heat, and as a result of there is a difference in the heat between these two or three resistance which are used there. So, there is a generation of electric current, and this electric current is measured and represented in the form of a peak. So, this detector has also some merits, because this is very, you can say this is also one kind of universal detector. So, this detector is simple, it can be used in almost all type of applications, and the advantage is that it is non-destructive type of the detector. So, thus it can be used for the preparative and fraction collection work, but the limitation sometime is that it has low sensitivity and low resistance, but otherwise this detector is also used in many of the applications of gas liquid chromatography. So, depending upon the type of the material we want to analyze, we have to choose the detectors accordingly. We will now see another kind of detector, that is electron capture detector. So, here again the name itself suggests that it is a kind of device where the electron capturing is done. So, it works on the principle of electron capturing, whereby various substances, that means different type of substances are used in this detector. It can be nickel, it can be other substances which are having the capacity to produce certain things. So, here it is based on the principle of electron capturing by various substances being sensed, which causes a reduction in the ion current. So, chemical containing an electron-active element, for example, chloropesticides. So, chemicals containing an electron-active element or group have a strong affinity for electrons. So, in the gaseous state, they tend to capture electrons to form negative ions, and exposing these compounds to a source of low energy electrons forms the basis of an extremely sensitive selective detector for such compounds. And here this electron capture detector is having very high sensitivity, and it is used in food industry or in agriculture. It is very commonly used in the analysis of organochloropesticide. The radioactive source which is employed in the electron capture detector includes tritium and nickel, and methane or argon are the gases which are generally used in this detector. So, this is again, as I said in my previous slides also, that choice of detector lies with the user, that what type of the compounds he or she wants to separate or wants to elute. So, here this detector is very commonly used for the nitrogen and phosphorus compounds, that means compounds which contain nitrogen and phosphorus. So, this detector is also sometimes called as flame thermionic detector. So, in this case, the principle of this detector is that the heated alkali, that is rubidium sulphate, emits electrons by thermionic emission, which are collected at the anode and thus produce ions. So, when a solute containing nitrogen or phosphorus is eluted from the column, the partially combusted nitrogen and phosphorus materials are absorbed on the surface of the bead, and this absorbed material reduces the work function of the surface, and as a consequence the emission of electron is increased, which raises the anode current, and this is measured as a signal. So, here basically the alkali source is heated and sample is brought in and undergoes some reaction producing ions. So, as evident in the flow chart given in the slide. So, this detector is again a sensitive detector, and it is generally used for the compounds containing nitrogen and phosphorus, and the sensitivity of the detector is about 10 raised to power minus 12 grams per ml for phosphorus and 10 raised to power minus 11 gram per ml for nitrogens. So, this was about the different type of the detectors. So, now we can conclude here that in case of GLC, the basic principle is the partition chromatography, where the different types of these materials, depending upon their partition coefficient, they are resolved and then detected by different types of the detectors, and use of detectors and injectors depends upon the type of analysis and the type of compounds we want to resolve. So, dear students, in this lecture we have learnt about the basic principles involved in the gas liquid chromatography. We have also learnt about the different components involved in gas liquid chromatography, whether they are detectors, they are injectors, what are the limitations of the detectors. We have also learnt about the different type of the columns and different type of the stationary phases which are used in the filling of the columns. Now we are prepared to start our work on GLC. I hope you people might have enjoyed the lecture and you might have understood the concept of gas liquid chromatography. To strengthen your knowledge further, I will suggest you 2 books which you can read and you can increase your knowledge about the gas liquid chromatography. The one book is Gas Chromatography by Follis, which is very interesting book, and another one is the Analysis of Food, which is edited by Nielsen. I hope you might have enjoyed this lecture, and I expect that we will meet in another lecture on another day. So, thank you very much.